Hello, welcome back to this channel. So today's video we're going to be looking at some more calculus, and more specifically we're going to be looking at how to derive the derivative equation. So this equation, it comes from somewhere, and basically we're going to walk through the concept of how it came about. And by doing this we'll be able to see a bit more why is it useful. So why do we take the derivatives? And in next videos, we're going to be looking at derivatives like more specifically. So this video is really purely just to understand the equation, like how it came about. So we're going to start with quite a simple example at first. So here we have an equation. Here we have f of x on our graph on a y and x axis. And you can see it has a point here, which is denoted as 2, 1. So x is 2 and y is 1. And basically what we want to do is we want to find the gradient of this line right here. And basically you can notice here that we usually use the equation here, rise over run, so how much it goes up and how much it goes onto a side, and that would be the equation of a gradient. But the thing is, if we use this example here, we actually only have one point, and so it's a bit like it's impossible to find the gradient of this line just knowing one point. And this is why we always use 2 points. So we're going to add it in. So we're going to use the point 4, 2. It can be any point on your curve. I'm just going to be using this one for today. So here, so you can see this point right here. Here it's on the line, and this one is, so basically the distance between the 2 points here has a certain gradient. And this is also a characteristic of a straight line, is that the gradient actually is the same the entire way through. And so we just need 2 points to be able to find it. And once we find the gradient between the 2 points, we can find it over the entire line. So we're just going to try and find that for this equation here. So first of all, if we use our rise over run equation, we might notice actually that first we need to see how much it rises. So between the 2 points, how much does it go in height? And for this, I'm going to write it on here. So basically here we're looking at so how much it rises, and we're going to annotate it onto this graph right here. So you can see between this point to this point, the y value increases, and this is the value that we want basically. And to be able to find it, let me show it to you. So basically to be able to find it, you need this distance. So it's basically the entire distance here that I'm showing with my mouse. And then you want to remove this distance right here, because you only want this one to be left. And so to be able to do that, you can do 2 minus 1, and that will give you the space in between. And then for the run, almost the same thing happens. So it runs from here to there. So basically it increases in the x value by a certain amount. And to be able to find that value, we can take the overall value, like the overall length, so from here, but then we remove this length right here so that we are left with this one that I annotated. So I'm going to show you how it goes onto the graph, onto the equation, sorry. So here 2 minus 1, you can see it's in green, so it relates to the rise or the y increase. And here we had 2 minus 1, so this here is our rise. And then for the run, we used the farthest value minus the closer value, so 4 minus 2, and that will give us the distance between the 2 points, but only on the x. So this is the y this is dx. And so if you simplify then this equation, this is what you could get. So 2 minus 1, 1, and 4 minus 2, 2. So we get 1 over 2. You can also simplify this to 0.5, but you don't necessarily have to. It's up to you. So basically what we get from this is actually our gradient for this line over the entire line is going to be 1/2. So whenever you increase your height by 1, it will actually go in length by 2. And that's going to be true everywhere. If we look at this section right here of the curve, you can see it increases by 1, but it actually increased by 2 in the x direction. So this is basically how we usually find the gradient for a straight line. And I want to introduce to you the same way, but we're not going to be using numbers, basically. So let me take it out. Okay. So here we have the exact same graph, but this time we're going to annotate it in a different way. So because in the previous graph, you realize that we knew the values, so it was easy to find an actual gradient. But so for this example, because we don't have any values, like numbers, we're just going to be using some different terms to do the exact same thing. So first of all, our point here, which was our original point, we don't know its x value, but we'll just call it a. Oops. Here. So this one we can just call it a. It's just a random letter. And then, so this is our x value for this point. But then you can see, so our point here has x value a, and for y value, we need something to show that it's this point specifically. And I may have mentioned it before, but you know how you can actually annotate y? You can also call it f of x. Oops, just like this. So y and f of x are actually the exact same thing, because f basically says that it's a function in terms of x. And this is what we're doing here. This is our this is a function in terms of x, not any other variable. It's just specifically for x. But this time, we know what our x is. It's not a number, but it's basically a. So a is our value, and so this y value here has to be in terms of this x value. So you can actually call it f of a, because now it's the same function. It's the function f of x, which we have here, but this time it's not, we know it's not just x, it's not any number, because it's specifically our a. And then for our second point, we can just call it b. And here, if you follow the same pattern I used for the first point, you might guess that actually the y value for this point here, you can simply call it f of b. So you see what I did here? I basically just renamed these points, but using terms that aren't specific. So a could be anything, b could be anything. But it's just to show that it's two different points for our graph. And you can actually annotate. So here I annotated this point, so you can see the x value is a and our y is f of a. And then the same thing can apply for b. So the x value is b and the y value is f of b. And so when we're using the equation for the slope or the gradient of the line, we can actually use these terms right here to make a more general equation. So we can use it. This is moving strangely, sorry. Okay, whatever. So let's use the exact same method we used before, but this time with our new terms. Move it up here. So for instance, our rise, which we can indicate like this. So it's going from one point to another, but only in the y direction. This one, we can see the larger value, the one on top here is f of b. Then we want to remove f of a. So we want the entire length minus the smaller length. And it will give us the difference between the two. So when we write it down, we can have f of b minus f of a. And then for the run part, we can have the same thing. So the run part is basically moving only in the x direction. And for this, then we have the larger value minus the smaller value. So we have the entire length here minus this length here, which will give us the difference between the two. So our difference here in run will be b minus a. So b minus a here. So this is now a more general equation to show the gradient. So rise over run, but using more general terms. So this is just a way to show you, because just now we're going to go into another example. It's just to get you a little bit used to not having just numbers. So having like different ways of writing it. So what you might have noticed then here is that to be able to find the gradient, we used 2 points. So we made our point here and this point here, and then from there we were able to use this equation, rise over run, and find the gradient. What if you were given a curve which is like this, so that it's curved? So you might see, for example, at this point right here that I'm showing, the gradient is quite steep. However, if you take the point here, it's not as steep. And so the problem is with this one is that actually the gradient changes over the entire curve. And so it is very difficult to just find one gradient and assume that it's the same one for the entire length. And so the thing is now, imagine we have a problem and then they start asking us to find the gradient at a certain point. So for instance, let's say for example, right here, we have the x value of this point, and then here we have the y value. So we're still using the exact same method that I used before, so this one we can call f of x. Because our x value, we just call x here. But this x is different from this one. This one is just to represent that it's the x-axis, and this one is just to show that it's a specific point. And so we have this point right here, and what if they tell you, okay, find the gradient of this point? And this is actually a bit more difficult than we might think, because actually if we looked at the previous example, like this one, we were able to find 2 points and just be able to find the gradient. With this one, we only have 1 point. So it gets a little bit more complicated. But it's not that bad, don't worry. So what we're going to do now is we're basically going to find a second point. We can just make up a point, because then from that point we'll be able to find the gradient between the two. So I'm going to put my point just 1 unit after. I'm just going to make it right here. You see? And then I'll make the y axis approximately here. But I still want to give it a name. And the thing is, you can see that the new point is a certain distance from the old point, but we don't know how much. So it's just a distance away. And so what we're going to do here is we're going to call it x plus h. H is just a random value, it could be anything. But basically h, do you see here? I'm just going to annotate it on the side so you don't forget. So this line right here in orange, this one is basically the distance of h. So this point is x plus the distance h. That's going to give us x plus h. So this point this is its new name. We're just going to call it x plus h. And now we've used this method to name the y point, so we're just going to use the exact same method. So here you can see we call it f of x plus h because this is our x value. We call it x plus h. So far we've just been using the same idea sort of as before. And so what we're going to do, I'm just going to show you here. So this point here, we call it x, the x value, and f of x, that's our y value. So this is the coordinates of this point here. How about this point? If you want at home, you can always like pause the video and guess on your own before you look at the answer. But this is the answer. So here, our x value is x plus h, because this is how we named it. And then our y value, then it's here, it's f of x plus h. So this would be the coordinates of this point here. I'm just going to make it a little smaller. It's still going to be there, but a little smaller because otherwise it takes up a little too much time, space. Okay. So we have our 2 points. This is great. And so basically now what we can do is, what if we trace a line from the 2 points? From our first one to the second one, we trace a line between the two that joins them straight. And if we find the gradient of this one, of this line here, it would be quite close to the one of this point that we're looking for. So we're going to start and do that. So obviously we're still using the rise over run. So this is the equation that we came about in the in the previous example. And so here we're going to plug in our new values for this example specifically. So what's going to happen here is, so the rise here, let's annotate it. So the rise here is this one. So this is our increase in the y. And we can see here it starts from, so the larger value is f of x plus h. And then if we remove f of x, we get the difference between the two. So we can write that down. So f of our x plus h, which is our larger value, minus f of x. So this is, here, that's a bit better. So this is our rise. This is how much it increases in the y value, so how much it goes in height. But then it goes a certain way along the x-axis as well. And this one we will annotate, so from here to here. And this one is the increase in the x direction. So our larger x value is x plus h. So we can write it here, x plus h. I'll just put brackets to make it a bit clearer. And then our second value here is f of x, is just x, sorry. So larger value x of x plus h, and our smaller one is x. So we can write x here. And then from here, we can actually simplify this equation. Yeah, ignore what's highlighted here. So this is what we found, right? And you can notice at the bottom here, we have x, so positive x, and then here we have a negative x. So these two can actually cancel each other out. And so we would just be left with h. So this is what we're going to write. Oops. So we have just h at the bottom. So this is our final equation. So this is the equation for the gradient of the straight line between the 2 points that we made up on this line. But now do you see how this is just an approximation, right? This is not exactly what we wanted, because we wanted the gradient exactly at this point right here, but not between the two. We just wanted it at one point. And so what we can try and do now is, we know the value of h that isn't really a number, it's just like an idea to show that it's farther away. So what if we actually made the distance of h smaller so that our second point that we made up would be a little bit closer? So therefore, the line that we make between the 2 points is also closer to the gradient of the point that we're looking for. And so you can see how if we make our h smaller and smaller and smaller, we can eventually get so close, like so close. So our 2 points would be so close from each other that it almost does not matter, that we can just ignore that it's just 2 points close to each other, and we can just say that it's definitely the gradient at this point and only this point. So this is what we're trying to do basically. We're trying to make this h value so small, so close to the first point that we can just ignore it. And if you watched the video that I made right before, so what is a limit? So the link will be down in the description. I really recommend that you watch it because this will make so much more sense. And so basically what we're trying to do is we want the value of our h to approach 0. We want it to be no space, like that h does not exist anymore, that there is only no space between the 2 points, that it just makes it 1 point, and then we would be able to find the gradient. And so this is where the concept of a limit is coming in, like quite handy. So let me show you how it works. It's really not that hard, I promise. So here is our final value, our final equation that we found, but we're gonna add a little something. So I'm gonna add, nope, sorry, where is it? Here. So I'm gonna use a limit. So yeah, really please go watch the previous video, it'll make a lot more sense. So we want that our h value, we want it to reach 0. So we can just write it here. So as h, let me have an arrow here, as h approaches 0. So this is what we want basically. We want to use this equation, but when our h value is getting so small that we don't want it to exist anymore. And this is actually basically it. We're already done. This equation right here is the real equation of a derivative. They also call it the limit definition of a derivative. And this is because this equation right here explains what a derivative is trying to do, where you want to find the gradient, but only at 1 point. So you're basically having 2 points. They're so close to each other that the h space in between them is 0. So that you can just ignore that it's 2 points and only have 1 point. So technically speaking, yes, it is sort of an approximation, but do you realize that if you have a space between the two that is so small, like so close to 0, that in the end you can just assume that it is 0? This is basically what's happening. And this equation right here, even though you might not have seen it in your in the the formula booklet that's given by the IB, you this equation basically, you can notice how if we plug in a value of x and we solve for it, so our h's will go to 0. If we solve for it, we'll basically get the gradient is only at this point right here. And what people did then basically is they took this equation right here and they plugged in almost all the values of x that they could find. So by having so many values and finding the gradient at so many different points, they started actually noticing some patterns. And the equation that you have then in your booklet for a derivative is basically an equation that they were able to find using this equation. So this equation was able to find the gradient at specific points, and so they basically found a pattern, and so they made the other equation to be able to find it so much quicker. So this is why this equation right here, if you're doing the IBAI math, this is not for you to remember. You don't need to remember this. This is really just for you to understand how it works. So it's basically, yeah, so you understand what a derivative means, what it actually is doing. But then you're lucky, you'll just be able to use the other equation, the simplified form basically, and so you'll be able to find derivatives very, very quick. And so yeah, that's what we're going to do in the next video. We're going to do some more derivatives. So I hope this was helpful. Hopefully you understand a lot better what the meaning behind a derivative is. And I will see you guys next time for some more questions.